Laboratory 5, current sources and mirrors again. Okay, if we scroll down, there are two designs for you to perform. The first design is as shown here, a beta helper current source. And secondly, how the beta helper will actually help in performing some more complex output. The first circuit, figure 1, has emitter degeneration. We're going to do some calculations with that. The second circuit has emitter degeneration and area scale multiplication. Let's have a look at the specification for each two. VCC equals 8 volts, I reference 0.65 milliamps, I out 1.3. Scale ratio 2:1 output then. And on the opposite side we've got reference 200 microamps, output 300 microamps. Output voltage compliance should be 1 volt. Okay, so let's have a look at how we design this circuit. We need to calculate the volt drop on the Kirchhoff's voltage loop from here, through here, through here, and down here. So our Kirchhoff's loop is quite complex. For a start, we're going to have a voltage here, VE. Okay, and that's proportional to IE. I'll define what that is in a moment. IC will be here. We have a volt drop here. Let's label that up, VBE, Q6. We then have Q7. This is the clever device, you've seen this before. This is providing base currents for that transistor and base currents for that transistor. So the emitter current we approximate to being equal to the collector current. Once we know the collector current, we can calculate this volt drop here, which is VBE Q7. And finally we have the volt drop here, which is effectively V drop across our reference resistor. Okay, so let's work out how we're going to design that. If we know what our reference current is, we should also know what our collector current is. We're going to ignore the amount of current going into the base of Q7 because of the way the beta helper works. So IC is approximated as I reference. Okay. I out, in this case, is our prescribed value, therefore we can calculate the collector current in Q7. Let's go to the sheet and put these calculations together. We're going to need to start off with VE plus VBE I forgot what the number was. Q6 and Q7. VBE Q6 plus VBE Q7 plus VREF. Okay, equals 0. You're the designer, you're going to set that value. We're given the value of reference current, which will determine that value. We need to do a little bit of work here to find that term, and we know parts of that term. Okay, and of course we know the 0. Let's just write out VBE Q6. That's equal to VT natural log I reference over IS. Okay, brackets. So those are all terms we know, therefore we can calculate VBE Q6. We're going to design VE, therefore we can calculate that one. VBE Q7, this is a little bit more complicated. VBE Q7 is equal to VT natural log. Now I ref is the reference current divided by beta. So that's the base current that's supplied from that. Then we add in the output current. Okay, these are running at different values of current, so the reference is different to the output. Okay, so those are our two currents, and those two currents are now divided by IS. Okay, so note check. VBEQ7 is going to be substantively smaller than VBEQ6. Why? Because we've got divide through by beta here. And finally we have VREF1. Okay, VREF is actually equal to I reference R reference. Okay, we know I reference, we're going to calculate RF. Okay, and that's your design process complete. Okay, now I will note as well that what you're tasked with doing again is looking at the output compliance limit. So you should find out if there's a gradient, so you're designing for some initial value of load impedance. At some point in time it will stop working and start to tail off. Okay, that's RL maximum. Okay, so you're going to determine that. What I would like you to tell me is this gradient. You know, you've seen the basic simulation before with the basic mirror. What happens with the beta helper with emitter degeneration? Does this gradient improve, get worse, stay the same? Those are the big questions that you've got to answer today. Moving on. This circuit at first looks a lot more complex. It isn't. Area equals 2. Okay? Area equals 3. On professional CAD tools, we would write that next to our BJT, and all it would do is it would scale up each of the currents at each of the nodes. In OrCAD we can't do that, so we have to have transistors wired like this. The equations are exactly the same. You define your VE. VBE is proportional to the individual currents, so whatever the reference current is divided by the number of transistors. In this case we have 200 microamps. Therefore inside IC, for all purposes, we use 100 microamps. Okay, so you can now calculate VBE across this compound transistor. You would perform the same functions as we've done before, but now you're counting base currents on 100 microamps on all BJTs, and you would be able to calculate this value here, this volt drop. And we know the current here, so you now calculate this volt drop. Okay, so it's exactly the same design process. Here we have our output stage load, just the same, and in this case we have some sort of degeneration and again VBE. So inside here you have one big Kirchhoff's voltage loop. You could have different VEs on each side of the input and the output, or if you want to be a little smarter, all of these VBEs across all transistors will be identical if you keep the current densities the same. So the spec says the output current is 300 micro. As the output current is 300 micro, each BJT is taking, in effect, 100 micro. Okay, and as you come down here you see 100 micro. So everybody is taking 100 micro, therefore VBEs can be locked off, therefore REs are exactly the same, which means it's very easy to calculate. That's the kind of processes that you might use on an IC. So I'm not going to tell you any more about that circuit, I'll leave it for you.